No, you can leave it. I put it because she's coming back.
My first question for you. Okay, so y'all pay attention right now, and I'll tell you, like, you'll know when you need to write something down. Okay. How do you know the number of protons in an atom? The atomic number. Okay. Where do we find that? The top number in the box on the periodic table, right? Okay. How do we find the number of neutrons? Atomic mass minus atomic number. Where's the mass? The bottom number. Atomic number's at the top. So everybody's cool with that. We know how to do that. Okay. What about electrons? The atomic number? Why is it the same as the atomic number? Because these atoms are no, I said how do we know the number of electrons?
It's same as protons. It's the atomic.
And y'all said the atomic number is the same as the protons. Okay? And so it's like that because these are all neutral. In a neutral atom, the electrons are equal to the protons. Mm-hmm. Yeah. How do I know the difference between one element and the next? Like what determines which element it's going to be? Like why is nitrogen different from oxygen?
Different number of electrons.
Not valence electrons. They do all have different mass. But is their mass the thing that identifies them? No. What is it? Their what? Nope. Huh? No. Their number. Okay, so I guess I just assumed, this is my fault, not yours. I assumed we picked that concept up, but I learned today that we didn't. So, what makes one element different from the next is its number of protons. As soon as I add a proton, I get the next element on the table. Or if I take it away, I get the element that is before it. Does that make sense? Okay. So, when we talk about elements like that on the table, they're all just regular, normal, neutral, right? Sometimes they don't exist like this. Sometimes they don't exist like this. Okay? Sometimes their nucleus will have more neutrons or less neutrons. What do you think they'll be if that happens? Would they be the same element? Ooh, are we lost?
Wait, I missed the whole thing.
I know y'all are zoning out on me.
Yeah, I zoned out. I missed the whole thing he said.
Okay, I said sometimes their amount in their nucleus can be more neutrons or less neutrons. But then I asked you, would they be the same element? And some people said no.
Why would they be the same element if the time might change the charge of it?
Oh, did I change the charge of it? I said neutrons, so it's no charge. If I'm changing the neutrons, is it going to change the element? No. Because y'all told me, y'all just figured out what actually determines which element is which. What determines which element is which? Protons. Okay, we got a lot of stuff going on and a lot of faces that are kind of empty looking. Let's see. Okay, so watch. This is hydrogen, helium, lithium, beryllium, boron. As I added protons, the element changed. That's what determines the element you have. By the amount of protons, period. That's it. That's all that we need to know which element it is. Okay? So, let's go back. Let's look at one proton, no neutrons. Which element is that? Hydrogen. Okay, look at the table. What's the mass of hydrogen? 1. What is his number? 1 minus 1 is 0. This is regular hydrogen. And look what it says up here at the top. Stable. Okay? Now, what's the mass of hydrogen? 2. You were right.
I thought you can change the mass because of law of conservation of mass.
No. The law of conservation of mass is the mass that you have before a chemical reaction, you will also have after a chemical reaction. Where does the mass come from? The amount of protons and neutrons. What did I just do? I added a neutron. So this is called H2. Hydrogen is the only one that has a name for each of his. This one is like deuterium or something like that. It's in your notes. You should have copied it down. Y'all following where I'm at? As soon as he got a different amount of neutrons, this is an isotope of hydrogen. An isotope is when the neutrons are different. I can have more neutrons. I can have less. Either way, I'm an isotope. Everybody with me? Okay. This is still stable. Look at that. What's his mass? Louder. 3. Who doesn't understand? 3 minus 1 proton. How many neutrons does he have? 2. What else did you notice changed when I changed that? It's not stable anymore. It's radioactive. Everybody with me? We understand? Yeah.
If a neutron is neutral, then how can you make a stable element radioactive?
Okay. So, the nucleus likes to have a certain ratio of protons to neutrons. When it gets too much or too little, it tries to stabilize itself. If there's too much, it gets rid of them.
So being radioactive is what trying to do.
Being radioactive means I have an unstable nucleus and I'm trying to become stable. So write in your notes, radioactive equals unstable. If it is unstable, it's going to be radioactive.
It's causes, if you have enough of it, it's causes like a nuclear.
Yeah. Yes.
So that's what they do, like, to nukes.
Okay, so we're going to get to that. We're going to talk about that too. So the nucleus is trying to become stable. In this case, he would want to get rid of a neutron, and when he gets rid of the neutron, that's the nuclear reaction. What's going to be produced from that as well? Radiation. Yeah, radiation is going to be that. The waste is going to have that in it. Does that make sense? Okay, we're going to get into more of that in a second. Everybody's cool with this so far? Okay, so there's some different ways they write this stuff. What is this called right here? This. No, this is called isotope notation. This is called isotope notation. Let's do a few of those. What does this mean? Okay, how would we say it? Carbon 14. Okay, she said it means carbon has a, so the 14 is the atomic mass. Is this the regular form of carbon or an isotope? How do you know that? No, that's a good answer, but that's not why. No. Okay, so we got to look at the periodic table. What is carbon's mass on the periodic table? 12. What is this carbon's mass? This is an isotope.
So if it don't match, it's always isotope?
If it doesn't match,
Basically, if it doesn't match, it's regular mass in its isotope.
yeah, like the mass that's on there is like it's regular, like it's normal. This is gained. Okay? This is not actually isotope notation. This is isotope notation. Okay? So from this notation, I can tell the protons, the neutrons, and electrons. How many protons does it have? 6. If you're lost, you better speak up. How many neutrons does it have?
8. 14 minus 6 is 8.
The mass minus the number. Oh, you were one off, yeah. Electrons? Who has a question? What about this? Yes.
Protons are 6. Atoms and neutrons are 6. Electrons are 6.
Why is he the only one answering my questions? Who's lost, not understanding, has a question, something?
Okay. You said what you just wrote the little numbers on top of each other and that's isotope notation. So what exactly is C-14?
just another way they write it. They just don't call it isotope notation.
What is the exact reason?
I don't know.
I don't remember how to figure out.
Yeah, I'm like showing you all the ways that you can read. Like when they write their equations and stuff, it's written differently than what we're used to reading. So I'm showing you, I'm going to build up to get to the bigger equations. Yes? Okay. We're talking about isotopes. An isotope is when the nucleus has a different amount of neutrons. So carbon on the table, he has a mass of 12 and a number of 6. So 12 minus 6, he's going to have 6 neutrons. But this carbon right here, he has 2 extra neutrons. He's an isotope. Because the nucleus has a different amount of neutrons. Isotope, neutrons, change. I don't know how else to put it. That's the simplest way I can put it. Okay? So, they write isotopes in like these different ways. They'll put this, or they'll put like carbon 14. That's the same thing as that. Or they'll write it in this notation. In this notation, y'all had already written in your notes, you were supposed to already write in your notes all this stuff right here. Okay? In your notes, I didn't break it all down to say this is, like I'm trying to use what you already know to then figure out protons, neutrons, electrons from that notation. Y'all with me now? Okay, so I want to look at uranium. What is, how many neutrons would a regular, normal uranium have? Do y'all have a periodic table in your binder somewhere? Uranium, look, it's 92. 92. The bottom number is the protons. It tells you how to find it. Yes, it is on the bottom of the table. How many neutrons does the uranium on the periodic table have? Huh? How do we figure that out? 238 minus 92. It's 146. Okay? So, he is actually from 92 on, no, actually 84 on, they're radioactive. So as soon as I put him in like he is on the table, he's already going to read radioactive. Okay?
Is everything that's done in that section radioactive?
Huh?
Is everything that's done in that section radioactive?
No, because I said from 84 on.
Oh.
So is this whole piece radioactive? No, because I said from 84 on. That's in your notes that you already copied. 84 on is radioactive. 92 on is synthetic. What's that mean? Man-made. Yeah. Doesn't naturally.
So what are some of the
92 on. So uranium, Amera something. I don't know all of their names.
plutonium, plutonium,
Yeah, like they just keep on going. And even all the way to 118. Does that make sense? Okay. So, every time I'm changing the neutrons, it's a different isotope of uranium. Does that make sense? I can keep going. Okay, once it says not valid, it's not. It's from 215 to like, I don't remember how high up it goes. So each of these are a different isotope of uranium. And their half-life changes. Okay, we're going to learn about half-life.
Half-life is the ability for how long it lasts. Last year in our college class, we had to do that and to see how fast they react. Some react slower than others.
Okay, a half-life is the amount of time it takes for half of it to decay. So I start with 100. This one is 21 seconds. After 21 seconds, half of the uranium-223 will decay. In another 21 seconds, I would have 25%. I would have half of 50.
So it depends on, like, when you say it goes away from, like, vapor or something.
No. What happens is, in the nucleus, either some neutrons come out, and then I get a new element. We're going to learn about each type of decay tomorrow. Because if some of these neutrons leave, then my mass number is going to change, right? So then it's going to be a whole different element.
No, what I meant was, like, what I meant was when I said that, like, can you see what's going on? Like, when you said it was going away, would you be able to see it with the naked eye? Or would you...
No, you wouldn't. But if you, like in a nuclear bomb, when the explosion went off, the nucleus would be, you couldn't see the nucleus do it.
I mean, not the marshmallow.
No, yeah, like a nuclear, okay, so we need to talk about this. Who does not know about the nuclear bomb? Like, do y'all know, huh? Y'all don't know that we used a nuclear bomb.
Against, in World War II, against Germany and Hiroshima, that bomb?
Yes, we bombed Hiroshima. Do y'all know about this? No. You don't. Okay, that's what I need to know. All day today, they didn't know anything like about this.
They don't teach that.
Yeah, they do, but I don't know where they left it out for y'all. But yes, they do. Okay, so we bombed a little place in Japan, and then like the whole face of the earth right there was just like nothing. Okay, but miles and miles away, the people who still live from it, like they got cancer. They got the radiation. So in all of this stuff we're talking about, all of these forms produce radiation. Because the atom, the nucleus, ends up like splitting off. And there's so much energy that's released, it's released in the form of radiation. When these people, they ended up getting sick and dying. If they had children, they passed that mutation on to their children for years. Okay, so do you know that, how do they know the age of a dinosaur bone? Okay, everybody thinks that. Yes, the layer that the bone is in, we can say that they were in existence at the same time because the bone was on that layer and other rock layers come on top of it. But how do they know the age, the number? Can I look at a rock layer and say a number? No. We use radioactive dating. So what they can do is they can look at the bone or they can look at the rock. And they can see how much of this isotope has decayed.
They have to use that because not all the time is it corrected because of the layer. Like, disturbing to the ages and stuff.
Yes. But when if they like say somebody's out there digging and they find a mummy, how are they going to know how old it is? Radioactive dating. They take these isotopes and they know that it's going to take this isotope this many years to decay. We're going to learn how to calculate all this stuff. Yeah. We're going to learn how to calculate it. If I tell you it's been through 3 half-lives. Okay, 3 half-lives. In 1 half-life, 50% is going to decay. The amount of time it takes for half of its atoms to decay. 3 half-lives would be, no, you do half of 50, which is 25, half of 25, which is 12 point. And it's in percentages. Okay, and then it just keeps going, all of those numbers just keep going in a half and half and half and half. Okay? So, what about radiation treatment? Yes. No, not chemo. I said radiation. There is a difference. Y'all don't know anything about that? What's radiation treatment?
They like put radiation in them, like stuff that goes to the air.
It feels good and bad.
Yeah, it does.
Okay, so if someone has cancer, we're going to use radiation treatment. Basically what they're doing is they're sending that radiation into the cell and they're trying to kill the bad cell. They're also going to kill good cells. Well, yeah, but that can be a reason why they would get cancer again.
Doesn't it have bad cells keeping good cells in the packet? That's why it's in the
No, it's just that,
It's so strong.
yes.
Does it have radiation and X-rays?
No. X-ray is not as strong of a... They're all the same kind of wave, like it's one kind of wave. But X-ray is bad because it's so many waves hitting that bone per second. Radiation is a form like of gamma ray. Gamma. It's like way stronger.
So what about mammograms and stuff like that? Because I have
No, that's not.
those machines they use for it. Because some people.
Nope. No. A girl last hour said her mom went through treatment and the first time she was just like, they just put her in the little machine and like, that's where they send it in. The second time they gave her medicine and put her into the machine. So I don't know if like that meant it was stronger or not, but like she couldn't see her for, a few weeks. Because you would, and then the people who work with her, like the doctors and nurses, they're going to wear protective. Yeah, they're going to be protected from it.
I had one of my grandma one time. I wasn't able to go because something about my bones. I was too young. I was like 6 years old.
Yeah.
It affected my growth.
Yeah, it will. Like, you can't be around them until a little bit of time has passed. Okay.
It's like 3 different types, or 2 or 3 different types of radiation, right? Because it's like the radiation, like actual heat that you would get from a stove. Then
Well, that's thermal radiate. That's thermal radiation, basically. Yeah, but that's not going to hurt you. Everything that we're going to talk about when we talk about radioactivity is talking about the radiation that will hurt you, that can kill you. A nuclear bomb. Nuclear power plant.
How does that even work? Like, what do you even do with the power plant? Like,
They split the atom, they split the nucleus of the atom, and it makes so much energy that it will boil lots of water. And we boil water in almost every single form of production. We boil water to make steam, to turn a turbine, to turn a generator, to make electricity.
two questions, please. How does that?
We're going to learn about that too.
And can we?
Another one, a particle goes into the other one.
And one day, can we watch a video like that? Because I want to do this. Like,
Well, yeah, but everything that you would see is not like for real. I mean, you can't record that, is what I'm trying to say. You get what I'm saying? You know what I mean? Yeah, they have animations of it. I'm going to show you some different things.
Some of the health things that we have now is based from like generations of radioactivity, like mutations and stuff in the bloodline and attacking the cells and everything.
Oh, like us?
Like different things.
I mean, it could be an inherited trait, but the people who, from exposure, from the atomic bomb, that's what theirs was from.
yeah, because it was like stuff that was being released to the air, and then they got the radiation and the.
Yeah, I mean, it was released like people for miles and miles were like eventually died. They might not have died from the bomb that day, but like within a few years of it, like they were dying off because of it.
It's like because I watched a TV show when they was dealing with stuff like that, and I saw like if a nuclear bomb hit, for instance, if a nuclear bomb hit New Orleans, it would spread all the way like throughout. It would go from New Orleans all the way over to at least the end of Texas.
Yeah, there's like this, I think there's a site or something where you can put a pinpoint and say how far would it go if the bomb hit this exact spot, how far would all of the stuff go, and like it shows you the different layers. Like at this layer it would be like complete destruction, at this layer would be partial destruction, at this layer they would still have radiation. Like it's crazy.
And really, the impact on it be doing the most damage. It's like the shock wave and the radiations that come after that really do the most damage. Like they actually kill people because the explosion's only going to do so much just by like the mushroom cloud and then however far the fire goes.
I see what you're saying. Okay, so we've gone through all of this stuff. The last thing I need to talk about is this. When we learned about bonding, how does an atom bond? What does it do? It shares electrons, or it gives and takes. Okay? Nuclear, anything to do with nuclear or radiation, is a chemical change. But it's not the same chemical change that we've been learning about. Okay? In our chemical reactions, the change is in the electrons. In a nuclear reaction, the change is in the nucleus. That's the main thing y'all got to remember. Nuclear is in the nucleus. Chemical reaction that we've learned about, like bonding, it's in the electrons. Okay? Are there any questions? I don't know how I said it. Nuclear is changes in the nucleus. And if you have a chemical reaction, the change is with the electrons. Okay. So now y'all are going to finish copying your notes.